Hello everyone, welcome to the manufacturing processes class. In this video we're going to discuss the machining time and the metal removal rate of the various machining processes that we already have covered over the previous videos. These two parameters, the machining time and metal removal rate, they are very important quantities that we have to know how we can calculate them for the different machining processes. Very quick, as we're gonna explain the machining time. The machining time is the time needed to perform a certain cut or a certain machining operation of a certain work piece using a machining operation under a specific machining condition. We mentioned before that the machining conditions, these are the different machining parameters, which are three essential things, which are the depth of cut and the cutting speed, the speed of the cutting operation, in addition to the feed or the feed rate, the speed of feed operation of the machining operation. And we said that any machining process, it should have two essential working operations, or working motions. These working motions, one is the cutting motion, the second one is the feed motion. So the speed by which we are performing the cutting motion, this is the V, which is the cutting speed. The speed by which we are already performing the feed motion, this is the feed rate, as we explained before. In addition to the depth of cut, these three parameters define the machining operation or the machining condition. So for example, if we are performing a turning operation under a specific machining condition, so how long would it take for the machine, for the work part to be finished by machining? This is the physical meaning of the machining time. It's just to calculate how long it would take for a part to be finished under certain machining conditions by performing a certain machining operation. This is the machining time. Also, in addition to this machining time, there is another important parameter, which is the metal removal rate. The metal removal rate is simply the volume per unit time of chip removed of a metal part by machining, or in other words, how much volume that you gonna remove from the metal part per unit time, per 1 second, or per 1 minute, or per 1 hour. How much of volume that would be removed. As we mentioned before, what distinguishes the machining operation from any other operation is that during the machining operation, there should be a volume removal. It means that the volume should be removed, or a part of the volume of the entire material, the raw material, will be removed in the form of a chip. So it is important to know how much of volume that you are going to remove from the metal part per unit time. This is which is commonly known as the metal removal rate. So through this video, I'm going to show you how we can calculate these two essential parameters for the various machining operation. But the question is, what are the importances of, or why these two parameters are important for the machining operation? This one of the things, basically, we could use the calculation of the machining time and the metal removal rate to estimate the cost of the machining process. Like if you're going to manufacture a part by machining, this definitely would cost. Some of the cost is the time, how long it would take. As long as it's going to take a long time, it means that the cost should be higher. Also, the metal removal rate, if we are going to remove so much volume per unit time, definitely the cost of this product will be increased as well. So these two parameters would be used for the the estimation of the cost of the machining operation. In addition, we are using them for the design of the for the planning for the machining process. Like, what is the suitable tool that should be used for this work part? What should be the suitable cutting speed, the feed, the depth of cut that should be used to perform or to end up with this product with certain qualifications and properties. This definitely we need for this calculation to know the machining time and the metal removal rate. So these two parameters are very essential when it comes to the design and the calculation for the machining process and the calculation of the cost of the machining operation. That's why it is important to know how we can calculate them. And this is again the objective of this video, is to show you how we can calculate these two parameters, the machining time and the metal removal rate, for the various machining operation that we discussed before. Makes sense? So let us start with the turning operation. We mentioned before in the turning operation that you're going to have a cylindrical part, and this part is going to rotate. The rotational motion of the cylindrical part, which is going to be fixed in the spindle by a shock or whatever the method of fixing the tool into the lathe machine, as we explained before in the turning operation. Like this work part is going to rotate, the rotation motion of the part, this definitely is going to give us the cutting motion. So just a quick review of the operating principle of the turning operation, as we mentioned before, that you're going to have a rotating work part, assuming that this is the axis of rotation, this work part is going to rotate, and you're gonna use here a tool, a cutting tool. This tool is just gonna be moving parallel to the axis of the rotation. So this definitely is gonna give us the feed motion, and the rotation of the work bar, this is gonna give us the cutting motion as we discussed before, right? So the speed of the rotation of the work bar, this is the work piece or the work part. The speed of rotation, this definitely gonna define the cutting speed, and the speed by which the tool is already sweeping or sliding over parallel to the axis of rotation of the work bar. This is going to give us the speed of the feed motion or the feed rate, which is commonly known as the feed rate. So these two parameters are essential in fact. And if you have the tool is very slowly moving parallel to the axis, it means that this work bar to be finished is going to take a long time. Or if it moves very fast, it means that it will be finished very quick. So what does it mean? It means that definitely there is relation between the machining time and the feed by which this tool is already moving. Your objective is just to keep turning this entire length of the work part. So how long it will take in terms of time, this is the machining time that we would like to calculate. So definitely it will depend on the speed by which we're already moving the tool parallel to the axis of rotation of the work part. And some of the things that you should understand about the machines that you use for performing these machining operations, that the key idea that the cutting motion and the feed motion all the time they are related. So what does it mean related? It means that the transmission system inside the machine, and if you just have an idea or had a chance before to look at the transmission system of the machine itself, like you're gonna find that there is the gears that would be used for creating the cutting speed and the cutting motion, they are connected to the gears that would produce the feed motion, or the mechanism of the feed motion is related or connected to the cutting motion, and they already transmit the power and the motion to each other. It means that at the instant that you stop the cutting motion, that you're gonna find the tool will be stopped as well at the same instant of time. It means that they are related, or in other words, we're gonna say that the cutting speed, it is definitely related to the feed speed. So this relation, we have to understand it, and they already related through these equations. So if we are interested in calculating the machining time, this is gonna be the formula or the equation that we're gonna use for the calculation for the machining time. For actually, it is not just for the turning operation, which is the first operation that we're already discussing here, but in fact, you could consider that this is general equation for the calculation of the machining time for any machining operation, whatever it is. Because simply from the physics or dynamics, we knew that the time it should be length divided by speed or velocity, right? So the velocity here, which is F times N, this F times N, this term is commonly known as the feed rate. This is the speed of the feed motion. This is the speed by which that this tool will be moving parallel to the axis of rotation of the work part. So what does it mean? It means that the F times N, this gives the feed rate, which we could name it as FR, where R stands for rate, and where FR is the multiplication of the feed times N. What is N? What is the feed? The feed, this is the feed of the tool, and the feed, it is measured in terms of millimeter per revolution. So what does it mean this? This indicate, for example, if let us assume that the feed it is given by 0.1 for feed equals 0.1 millimeter per revolution. This indicates that when the work part completes one cycle of rotation, the tool will be moved parallel to the axis of rotation only 0.1 millimeters. If the feeder is 0.2 millimeter per revolution, it means that per one revolution of the work part, the tool will be moved 0.2 millimeter. So as you can see, the feed is related to the rotational motion. They are related together through the mechanism of the machine itself. All right. So the feed itself, here I'm talking about the feed, not the feed rate. Both we can name them, by the way, feed rate. We can name both of them feed. But the key idea is that what distinguish just feed from feed rate is the unit itself. The unit here is millimeter per revolution. But the feed rate, this is a speed, millimeter per minute. This is a speed. But this is kind of a speed, but related to the rotation. How much of feed that you're gonna give to the tool per one rotation of the work part. This is the feed. If the feed was given, we are interested here in the feed rate. This term is the feed rate. So we have to calculate the feed rate, which is the multiplication of F, which is the feed, in case that the feed was given in millimeter per revolution, and times N. What is N? This is the RPM, the rotational speed of the work part. The work part rotate, this is the current motion. So how much of a speed, what is the speed of the rotation of the work part? This is N. This N, it is RPM. RPM stands for revolution per minute. So what does it mean? It means that if you just count 1 minute over the clock, you're gonna and count the number of turns of the rotation of the work part, this is gonna give us N. Number of revolutions per minute. This is the N. In case that N was given, which is the current speed in terms of RPM, you're gonna multiply N times F, you're gonna end up with the feed rate, plug it here, you're gonna calculate the machining time. We didn't discuss what is LC yet, but I'm gonna explain it to you. But in many of the cases, and this is one of the things that you should understand about the machines that used for the machining operation, that the cutting speed, in many of the cases, it is defined in terms of V. So V, it is the cutting speed, and N as well, it is the cutting speed. Both are cutting speed, but the difference between N and V is the unit. That the N, it is revolution per minute, but V, it is meter per minute. Make sense? It is meter per minute. So that's why this is what commonly happens. Like in many of the machines, if you're gonna go to the control panel of the machine tool for a lathe machine or a drilling machine or whatever it is, that you're gonna find that all the time the control panels about the feed, it is defined in terms of millimeter per revolution, and the cutting speed, it is defined in terms of meter per minute. So the question is, in case that V was given to you, here we need N, not V. Both are the cutting speed, but the difference is the unit, right? So we need the cutting speed, but in terms of revolution per minute. In case that it was given to you in the problem in terms of meter per minute, you have to convert it into revolution per minute by multiplying V times 1000 and divide by over D0. What is D0? This is the diameter of the work part. Because in the objective of the turning operation, as we discussed before, is to decrease, the main essential objective of the turning operation is to decrease the diameter from D0 to D1, or to a lower diameter. So here we already dividing by the original diameter. This is the original diameter of the work part that you have. So the problem will be given to you in this form. Like we do have a work part that we would like to decrease its diameter from, let's say, 100 millimeter to 90 millimeter. So D0 will be 100 millimeter, and you're gonna plug it here. You're gonna calculate N, multiply N times F. You're gonna end up with the denominator to calculate the machining time. Make sense? How about LC? LC, it is the length of the cut. How long of the work part in terms of length that should be cut from the work part by turning operation. Like the work part would be of a length, let's say 1 meter, but it is not necessary to cut the entire 1 meter. You can cut just a simple part or a part of the entire length of the work part. So the LC, it should be the exact part that you're gonna cut from the work part or the work piece. This is the LC, and this LC depends on lots of things. Like for example, one of the things that we have to give like an approach distance before the work part, and we have to give, like, especially if we're gonna cut the entire length, we have to add like over travel distance. So I'm gonna explain to you these two distances very quick here over this drawing. Like assume that this is the work part that we would like to do machining for by turning, and assume that we're gonna turn the entire length. So assume that this is the length L of the work part, and we're gonna do turning for the entire length. So this is the LW, which is the length of the work part that should be cut. So when we decide to do turning operation, the tool, it is, so what should be the turn? We are planning to cut or to turn all the length, the entire length. But the tool, it should be starting, let's say, from a distance away from the start of the tool, let's say with from let's say 2 millimeters up to 5 millimeters away from the start of the work part. This distance is known as approach distance. This is approach distance. It would be given. If it is given, you're gonna add it to the total length. If it is not given, you're gonna consider it is 0, right? Then you're gonna apply the feed. So the tool will be continue moving, feed till the end of the tool. It doesn't make sense actually to stop exactly at the end of the tool, because we are not sure that we probably miss some small portion of the work part that won't gonna be cut by turning. So we have to skip over the edge and we have to override. So we have like over travel distance to make sure that we already completely formed or cut the entire workpiece length. So that's why we're gonna have, in many of the cases, we are applying like another over travel distance beyond the edge of the work bar to make sure that we didn't skip any parts that without any cutting at the end of the workpiece. This over travel distance also is like around 2 millimeter to 5 millimeter as over travel distance, over travel distance. So also as well, like the approach distance, if the over travel distance was given to you, you're gonna add it to the entire workpiece length. You're gonna end up with the total length that should be cut. So we're gonna say that, we could say that this LC, it is in fact the length of the work part plus the approach distance plus the over travel distance. If these approach distances and over travel distance were given to you, you're gonna add them to the total workpiece part. If they were not given, you're just gonna assume that they are zeros and you're just gonna substitute with the work, with the length of the work part that should be cut. Plug it here, you're gonna calculate the machining time in terms of minute. Why minute? Because you already substituting with N in terms of revolution per minute. Why this was given by revolution per minute? Because V will be given to you in terms of meter per minute. So if you multiply time 1000 by D divided by D0 square, this 1000 to convert the millimeter, because this is in millimeter, and the V will be given in meter. So to have consistency in the units, we had to multiply times 1000. So this 1000, it is a unit conversion. This is just to convert from meter to millimeter unit conversion. You're gonna substitute, plug here, you're gonna end up with the machining time, which is the time needed in terms of minute. How long in terms of minute that for this work bar to be finished by machining under these machining conditions, under this feed and cutting speed, how long it would take. So this is the first parameter, which is the machining time, how we can calculate it for a turning operation. The same thing for the meter removal rate. The meter removal rate, it would be calculated using this formula, which is V. Again, what is V? This is the cutting speed in terms of meter per minute, which would be given to you, times feed, which is millimeter per revolution. You have to distinguish between FR and F, N and V, and know exactly which parameter that you should substitute or use for both equations. Here we have to use F and N. Here we have to use F and V. What is D? This is the depth of cut. What is the depth of cut? This, as we explained before over the previous videos for the turning operation, the depth of cut, it is the penetration of the tool inside the work part. And this depth of cut can be calculated at the difference, as half the difference between the original diameter of the work part and the final diameter. Like for example, we would like to perform a turning operation of a cylindrical part and decreasing the diameter from 100 to 90 millimeter. So the depth of cut, it should be 5 millimeter. How? It means that you have to push the tool inside the work part, and the tool should cut from the work part 5 millimeter. And since the work part is already rotating, so we are removing 10 millimeter from the diameter. We are decreasing from 100 to 90. So the difference, it is 100 negative 90 over 2. This gives the depth of cut by 5 millimeter. If you multiply the depth of cut times the feet times the V, you're going to end up with the metal removal rate, but you have to make sure of the consistency of the units. Like if this diameter, of this depth of cut in millimeter, and the feed rate, it is in terms of millimeter per revolution. Per revolution, it is like kind of nothing in terms of units. And you do have this one in terms of meter. It will be given to you in terms of meter, so you have to multiply it times 1,000 first to convert it into millimeter per minute, and you're gonna plug it here. So you're gonna end up with millimeter cube per minute. This is gonna give us the metal removal rate. Make sense? So this is simply how we can calculate the machining time and the metal removal rate for the turning operation. So we explained these equations. Now let us consider some examples on as a practice on how we can make use of this equation to calculate the machining time and the metal removal rate for various turning operation, starting with this example, example 1. So let us consider this example of a mild steel rod. So this is the material of the rod, and based on the previous equation that we calculated the material of the steel part, or the material of the part, that it will be turned down from 50 millimeter to another diameter like 45 millimeter as given here, that the material type, it won't gonna affect the calculation of the machining time or the metal removal rate. So we don't care about the material that much for these parts. But anyway, it is made of mild steel. This is one of the material types of steel, or one of the categories or types of the steel. And it is rod. It means that definitely it seems that we're gonna work on turning operation having 50 millimeter diameter. So this definitely is gonna be D0. This should be the original diameter of the part, which is already given. If we just extract the given data here, we do have the original diameter is given by 50 millimeter. So how about it? And 500 millimeter length. So this is going to be the length of the work part. The length of the work part was given by 500 millimeter. Is to be turned on a lathe machine. Lathe machine, this is the name of the machine, and turned, it means that we're already working as turning operation, because one of the things that you have to know exactly what is the type of the machining operation that you are going to apply for the given problem. As already given here, turning or turn it down to another diameter, and lathe machine, this indicates that we're already working over a turning operation. And determine, it is required to calculate the machining time, which is TM, to reduce the rod to 45 millimeter in one pass. So we're gonna perform it in just one cut, one time. And it is required to calculate the machining time, how long it would take to perform to reduce the diameter from 50 to 45. So the 45 millimeter, this is going to be the final diameter, which is going to be 45 millimeter. In one pass, when the cutting speed was given by 30 meter per minute. As I mentioned before, the cutting speed, it would be given as N or V. What distinguish whatever it is, N or V, this mainly depends on the units. You have to figure out the unit, keep eye on the unit. Here it is given as meter per minute. This is V, not N. So the cutting speed was given in terms of V, which is given by 30 meter per minute. And the feed, as well the feed, it would be in terms of FR or F. This what distinguish whatever it is, FR or F, this depends mainly on the unit, which is given here by 0.7 millimeter per revolution. This indicates that this is just a feed, that it should be multiplied times N to be converted into FR to be feed rate. So it is 0.7 millimeter per revolution. Make sense? So this is for the given data, and again it is just required to calculate the machining time. So I'm gonna add, in addition to this machining time, I'm gonna calculate let us calculate the machining time, how much it is, and let us calculate also the metal removal rate, how much it is. Although the metal removal rate for this example was not required, but I'm just gonna explain it explain to you how we can calculate it. So the calculation is very simple. Your objective is just to start by writing the equation and figuring out what are the parameters that you have to get to form the machining time. So the machining time, it should be LC divided by FR, and we said that the FR is the multiplication of F times N. Make sense? F was given to us, so we need to calculate N, because N, which is the carrying speed, was given in terms of V, so we have to calculate N first. So what should be N? N should be 1000 times V divided by D0. Why D0? This is the original diameter that we already have here. Why D0? Because we need to calculate the minimum carrying speed, because as you're increasing the diameter, this N will be decreasing. Anyway, so this is gonna give us 1000 times V, which was given by 30, divided by over the diameter, which is D0, was given by 50. Doing the calculations, you're gonna end up with N by 1000 times 30 divided by 50 divided by the pi. This is gonna give us 190.98 revolution per minute RPM. Then your objective is just to plug this in, but we still need to calculate LC to calculate the machining time. LC, which is the total cut length, which it should equal to the workpiece part plus the approach distance plus the over travel distance. Did he give any idea or any data regarding the approach distance or the over travel distance? No, he didn't give anything. So I'm just gonna assume that they are just zeros, assuming that we're gonna machine the entire length, adding no approach or over travel distances. So in this case, we're gonna consider like 500 millimeter. This is gonna give us the LC. Then your objective is just to substitute into the machining time. So we're gonna end up with the machining time will be LC. We got it by 500 divided by F as given by 0.7 times N that we just calculated by 190.98. This, doing simple calculations, you're gonna end up with the machining time divided by the 500, or with the 500, this is gonna give us 3.74 minute all the time. If you stick to the dimension the same way that I just explained, you're gonna end up with the machining time in terms of minutes. So simply, this is the first requirement, the machining time. Very simple thing, straightforward problem. And here we're gonna calculate the meter mover rate, which should be V times F times D. V, this is the cutting speed, but remember that I have to convert it from meter per minute to millimeter per minute. So we have to multiply it 330 times 1000. This is to convert from meter per minute to millimeter per minute. So we're gonna have consistency in the units. The feed was given by 0.7 millimeter per revolution times D, which is the depth of cut. So here we have to calculate the depth of cut. To calculate the depth of cut, D, it should equal to D0 negative D final divided by 2, as we explained before. So we are going to decrease the diameter from 50 to 45. So it is 50 to 45 over 2, but we're gonna do this reduction in just one pass. It means that this total depth of cut will be applied at once, only one time. So this is gonna give us 2.5 millimeter, and then we're gonna plug it here. So substituting here with the 2.5, we're gonna end up with the metal removal rate will be something in terms of millimeter cube per minute. This is gonna give us the unit of the value for the metal removal rate. So this is gonna give us the 30 times 1000 times the 0.7 times 2.5, which is gonna be 52,500. So it's gonna be 52,500 millimeter cube per minute will be removed of the work part. This is gonna give us the total removal rate for this work part. And that's it for this example. Make sense? So it is, as you can see, it is very straightforward example, and all the examples are the same. Your objective is just to write the equation, figure out what was given, what you have to calculate, then direct substitute. You're gonna end up with the required parameter. Make sense? So this is for this example. Now let us move to example 2. Example 2 is also very similar. Like we do have 150 millimeter long, so this definitely is going to be the length of the work part was given by 150 millimeter and 12 millimeter diameter stainless steel rod. So the diameter D0, this is the original diameter, 12 millimeter. All the time he starts by describing the original dimensions of the work part, and then he tells us what are the type of the operation and what are the new dimension that we're going to end up with upon performing this machining operation. So he started with describing the original dimensions of the rod by 150 millimeter length or long and 12 millimeter diameter stainless steel rod is to be reduced in diameter to 10 millimeters. So this definitely is going to be the final diameter, 10 millimeter, by turning on a lathe in one pass. So we're still working in one pass, one single pass to perform this turning operation. And here we are talking about turning operation. So I have to use the equations that we described for the machining time and metal mover rate for the turning operation. The spindle, here he talks about the spindle. The spindle rotates. Something that you should understand, as we just explained, that in the turning operation, the work part is the thing that is going to rotate. Right, and to rotate it means it should be fixed to the spindle of the lathe machine, and the rotation of the spindle definitely is going to give us the rotation, the same rotation of the work part, because they are fixed together, so they are rotating together. So here he talks about the excuse me, the rotation of the spindle. So this rotation, it should be the rotation speed which was given by, or the which definitely should be the cutting speed. So he didn't directly tells us that this is the cutting speed, but we have concluded this thing that, or we have to understand that this should be, that the rotation of the spindle, it is the cutting speed. They are the same thing, right? So whatever he directly tells us that this is the cutting speed or the rotation of the spindle, both are the cutting speed, which was given by 500 RPM. We said that the cutting speed would be given in terms of V or N, depends on what? Depends on the unit, stick to the unit. So it is RPM, it means that this is N. So N was given by 500 revolution per minute. And the tool is traveling in an axial speed of 200 millimeter per minute. So the travel of the tool, this is the feed motion, right? We said that the movement of the tool parallel to the axis of rotation of the work bar, this is the feed motion, and the speed by which the tool is moving, this is the feed rate or the feed speed. The feed speed, it would be given in terms of feed as millimeter per revolution, or it would be given as millimeter per minute as feed speed or feed rate. This depends on the unit. So here, instead of describing the motion of the or telling us directly that the feed motion is given by this value, he said that the tool travels by this speed. So you should understand that the travel of the tool, the speed by which the tool is traveling, this definitely the feed. So he here indirectly gives us the feed as 200, and since the unit is millimeter per minute, definitely this is going to be the feed rate. And you should understand that he directly gives us the multiplication of F times N. F, which is revolution per minute, was not given. Instead, he gave us the 200 millimeter per minute as feed rate. It is required to calculate the cutting speed. How much is the cutting speed, which is V? How much it is? We need to calculate it. Also, how much is the metal removal rate, which is MRR? We need to calculate it. Also, how much is the time required for the machining, the tool steel, the steel rod. This is the machining time, how much it is. Make sense? So these are the three requirements. So we have to solve this equation in this form. So again, he requires the cutting speed, which is V. He requires the metal removal rate, or how much of volume that it would be removed per unit time. This is also the metal removal rate. How much of the time required to perform the machining operation or to machine the steel rod. This is the machining time, how much it is. Make sense? First of all, to calculate V, we already knew that N equals 1000 times V divided by pi over D0, right? So how much what should be V for a given N? Definitely is going to be pi D0 N divided by 1,000. This 1,000 to give it in meter per minute, as we mentioned, because this is the standard thing for all the machining operations. So this is going to give us pi times d0, which is already the original diameter was given by 12, the n, which is 500 revolution per minute, divided by 1,000. Doing the calculations, you're going to end up with something in terms of meter per minute. So this is going to give us 500 times 12 pi divided by 1,000. This is gonna give us the 18.84 or 85, actually it is 85 meter per minute. This is gonna give us the cutting speed, and this is the first requirement. Then what? So this is the first requirement. Also, now let us move for the calculation of the metal removal rate. You can calculate the metal removal rate, or you can calculate the machining time. It doesn't matter which one first. The metal removal rate, it is VFD, right? Which is V, which is the cutting speed that we just calculated. Depth of cut, we need to calculate it. Also, we need to calculate F, which is millimeter per revolution. To calculate F, he gave us FR equals F times N, right? So what should be F? F, it's gonna be the division of FR divided by N. FR was given by 200 millimeter per minute divided by 500. This is gonna give us 0.4 millimeter per revolution. This is the F. So we calculated the F we needed. We're gonna use it. So how about D? The depth of cut, it should equal d0 negative d final over 2 in one single pass. It means that we're gonna perform the turning operation at once. We're gonna apply all the entire depth of cut, which we're already decreasing the diameter from 12 to 10 millimeter. So it's gonna be 12 negative 10 divided by 2. This is gonna give us 1 millimeter as depth of cut. Make sense? Plug all these data here, you're gonna calculate the metal removal rate. So MRR is gonna be the V that we just calculated, 1885 times 1,000 to convert, this is just V, to convert the meter into millimeter times. Don't forget, most of the students forget this 1,000. Make sure that you have consistent units. Whatever, put all the units in meter or millimeter, it doesn't matter, but the key idea, make them consistent. So since we have F as millimeter and the depth of cut in millimeter, so I'm gonna convert this M as well into the millimeter by multiplying times 1,000, and this is what I've done. And then we're gonna have the F, which is 0.4 times 1. Doing the calculations, you're gonna end up with the metal removal rate with this value, which is going to be the 7,539.8 millimeter cube divided by minute per unit time. This is going to give us the metal removal rate, and this is the second requirement. Then he asked us to calculate also the machining time, TM, how much it is. So the machining time, it should equal to the LC divided by the feed rate, which was already given to us, so there is no need to calculate it. It was directly given as F times N by 200 millimeter per minute, but we still need to calculate only one thing, which is LC. LC is going to be the length of the work bar plus the approach distance and the over travel distance, but these two distances were not given to us, so they are zeros. So, and the length of the work part was given to us by 150 millimeters, so it is just 150 millimeter. This is going to give us the length of cut. Then plugging here, you're going to end up with the machining time as 150 divided by 200 millimeter per minute. Doing the calculations, you're going to end up with the machining time as 0.75 minute. Just a part of a minute that is needed to accomplish this machining operation. Make sense? So this is for this example. Also, it is kind of a straightforward example. The big difference, or the essential difference between example 1 and example 2 is in the given data. Here I directly mentioned cutting speed and feed, but there I didn't directly. I give this cutting speed and feed indirectly by describing them. I told you that he tells us here in this example we do have a spindle rotation. This here indicate that we indirectly talking about the cutting speed. the tool is moving or traveling parallel to the with an axial speed. So the movement of the tool, this is definitely the feed motion. So instead of giving the feed and cutting speed directly by their names, he described them indirectly to understand that they already the cutting speed and the feed, as we explained over this example number 2. Make sense? Now let us move to the last example for the turning operation here, which is example number 3. Alright, so the difference between this example and the previous two, actually, that in the example 1 and 2, the turning operations were done over one single pass. But here, we're gonna split it into two passes. It means that we have to split the problem into like two different problems. Like here, we're gonna perform the turning operation over two passes. This is the difference between this example and the previous two. The previous two examples, we performed the turning operation over a single pass, one pass. Make sense? So as long as you do have two passes, your objective is just to break down the problem into like two sub problems, and you're gonna deal with them like two separate problems. So how we can do it? Your objective is just to extract the input data or the given data for pass 1. Then you have to work over pass 2 as well, right? Define the things that you need for pass 1 and pass 2. What are these things? You need to know the depth of cut for pass 1. You need to know the feed for pass 1. You need to know the cutting speed for pass 1. The same thing for pass 2, like you set up two separate problems. That to calculate the machining time and metal removal rate, you need these three quantities, F, V, and D. You need them. In addition, you should know what should be the original diameter and the final diameter. So definitely if you know the original diameter and final diameter in pass 1, in addition to the V and F, you are in a good shape. You can calculate the machining time and metal removal rate for this pass, then you're gonna repeat for the second pass. Make sense? And this is what we're gonna do. So let us read the problem here. A mild steel rod with 50 millimeter diameter. So this definitely is gonna give us, this should be the original diameter D0, 50 millimeter, and 400 millimeter length. So this should be the length of the work part. Is to be turned on a lathe, so nothing new. Determine the machining time, which is TM, how much it is, and the metal removal rate, how much it is, MRR, to reduce the rod to 45 millimeter diameter. So this should be the final, but the problem is it should be done over two passes. So we have to split it into two passes. It means that in pass 1, we should know what should be D0, which definitely we're gonna start in the first pass by 50 millimeter diameter. But the D final in the first pass, it won't gonna be the 45. Because if we're gonna finish if we decrease the radius, the diameter up to 45 millimeter in one pass, in the first pass, so there is no room for the second pass. So it means that we are going to decrease the diameter to a certain value, which definitely should be bigger than the 45 millimeter. Then we're gonna end up with the 45 millimeter after the second pass. So how much is the final? We don't know yet. And we should know how much is the V, the cutting speed, the feed for the first pass. The same thing that we have to set up the same issues, but for the second pass, for pass 2. For pass 2, we should know how much is D0. Definitely something that you should understand here, that the D final of the first pass is gonna be an initial diameter for the second pass. Like the final diameter of the first is gonna be the start diameter of the second pass. Make sense? That in one pass you're gonna decrease from 50, for example, up to 46. Then you're gonna decrease from the 46 up to the 45. So the 46 will be the start for the second pass, will be D0. So D0 and D final of the first pass is gonna be the same D final, D0 of the second pass. Make sense? So how much is this D0? We don't know yet, but definitely we are pretty sure that we have to finish it up to the 45 millimeter. Make sense? Also, how much is V? How much is F? We don't know yet. So we have to figure out this data. Something also that you should understand, that we probably may perform the turning operation of the first pass and the second pass with the same cutting speed and the same feed. So if V in both passes would be the same, if on both passes would be the same, or they would be different, right? So this depends on the given data here. So let us continue reading the problem. That in the first pass, he gonna describe the first pass here. The work part is rough turned, but in the second pass, it is finished turning. So what is the difference between rough turning and finished turning? Rough turning, it means that we are not interested in or performing the turning operation and to be end up with a good surface. We don't care about the surface of the work part as much as we care that we would like to finish the turning operation. But in the finished turning operation, we are in interest to make the surface very smooth. So finished turning operation, it means that the objective is to decrease the radius, yes, but in the meanwhile, we have to achieve that the surface of the work part should be very smooth surface, very finished surface. But in the rough turning operation, we are interested in finishing the work part. We don't care about the surface, whatever is going to be smooth or not. Something that you should understand in general for any machining operation, whatever it is. And we already discussed these things very quick before over the previous videos. Like to have a finished surface, we said that we do have three essential machining conditions, which are the depth of cut and the feed and the cutting speed and the feed. These three parameters that what control the quality of the surface. So what does it mean? If you need a rough surface, or in other words, if you need the surface is very finished surface, very good surface, you have to decrease the depth of cut, increase the cutting speed, and decrease the feed. But if you did the opposite, you're gonna end up with a rough surface. So rough surface, it means that you have to increase the depth of cut, decrease the cutting speed, and increase the feed. Make sense? Someone would say, okay, so why do I need to have a rough surface? No, we don't need to have a rough surface, but we need to finish the work part very quick. We have to save time to save cost. We said that the machining time is related to the cost. As we took long time, this means more cost. So basically, to end up with a finished surface, we finish most of the part very quick by rough cutting, by increasing the depth of cut and increasing the feed, and we're gonna have like a little bit decrease in the velocity of the cutting speed, or the cutting speed will be decreasing somehow to finish the part very quick. This rough finishing will take like we're gonna finish most of the part. We're gonna decrease the diameter from 50, let's say, up to 45.5 millimeter. So we're just gonna leave only 0.5 millimeter of the diameter that it will be removed by finishing. Finishing is gonna take long time. Why? Because we are decreasing the depth of cut and the feed. It means that it's gonna take longer time to be done. So have to keep or leave only a small part, a few part of the metal to be removed by finishing, to make sure that the surface is gonna be super finished. And all the time the finishing pass or the finishing operation should be done after the rough turning. That we have to do rough turning first, then finishing after that. So that's why in the first pass we're gonna do rough turning. It means that we're gonna remove lots of metal, but we won't gonna decrease up to the 45 millimeter. We're just gonna leave, let's say, 0.5 millimeter at the end to be removed by finishing. So this will be explained as already given here. So in the first part, or the first pass, the work part is rough turned at a speed. So this is the cutting speed. Here we are talking about the first pass. So the cutting speed in the first pass was given to us by 30 meter per minute. So it is 30 meter per minute. And the feed, millimeter per revolution. So the feed was given by 0.6 millimeter per revolution. This is in the rough cut. But how much is the diameter? We don't know yet. We're gonna decrease the diameter from 50 up to how much? We don't know. He didn't give anything regarding the depth of cut to know how much is defined. But in the second pass is finished turning operation with 0.5 millimeter depth of cut. It means that we're gonna use 0.5 millimeter depth of cut to perform the finished turning operation. So if we calculated the depth of cut, the second depth of cut for this second path should equal to D0 negative D final divided by 2, which should equal to 0.5 millimeter as he gave us. He didn't give us the depth of cut of the first path, right? So how much is D0? D0 should equal to this D final, and we don't know both of them, but this D final here for the second pass was given by 45 millimeter. We would like to end up with 45 millimeter diameter rod. So if we did the calculation, you're gonna end up with D0 will be 46 millimeter from this equation. Do the multiplication times 2, move this one to the other side, you're gonna end up with 46 millimeter D0. So it means that this D0 here, it should be 46 millimeter, and which it should equal to the same D final as 46 millimeter. So what does it mean? It means that in the first pass, we're gonna do a rough cutting, rough turning from 50 up to 46 millimeter with this cutting speed and feet. But in the second pass, we're gonna decrease the diameter from the 46 millimeter up to the 45 millimeter given to give a depth of cut of a half with a cutting speed. The cutting speed here, continue reading, the second pass is finished turning off with 0.5 depth of cut and cutting speed with 20 meter per minute. As you can see, the cutting speed has been decreased to give a finished surface. And feed of 0.05 millimeter per revolution. Make sense? I'm sorry. Here the cutting speed was decreased. The cutting speed is not that it doesn't affect, but in many of the cases, to have a finished surface, it is recommended to increase the cutting speed and decrease the depth of cut and the feed. The depth of cut in the second pass, it is only 0.5, but the depth of cut in the first pass is going to be 4.5 millimeter. The feed, it has been decreased. Here the cutting speed was decreased, yes, but we still gonna end up with a finished surface. The key idea is to decrease the depth of cut and the feed motion and the feed, and this is what we did here. But also in the meanwhile, it is recommended to have a high cutting speed, but this depends on other measures that depend on the quality of the tool that it would be used and other measures. So it is not essential in many of the cases to decrease the cutting speed, but in most of the cases we are increasing. It is not essential to increase the cutting speed, but in most of the cases we are increasing it. Make sense? So it doesn't matter anyway, you're just gonna deal with this problem like two separate problems. So your objective is just to calculate the machining time and metal removal rate for these two problems. So what you're gonna do, you're just gonna work on pass 1. On pass 1, we do have here, we would like to calculate the machining time. So the equation for the machining time is LC divided by F times N, right? Since F was given, so we have to calculate N. N it is 1000 times V divided by pi D0 for pass 1. So it's gonna be equals 1000. The cutting speed for pass 1 was given by 30 meter per minute divided by pi times D0, which is the original diameter, was given by 50. So we're just gonna do the calculation. This is gonna give us 1000 times 30 divided by shift pi divided by 50. This is gonna give us 190.98 revolution per minute. This is gonna be V, and and LC, it should equal to the LW plus over travel and approach distances, which already will be zeros because he didn't give anything regarding these two distances. LW, which is the length of the wall part, was given by 400 millimeters, so it is 400 millimeter as given here. Then you're gonna plug these two data here to end up with the machining time TM for pass 1. So I'm just gonna add here subscript 1 to indicate this is pass 1. So it's gonna be the 400 divided by the feed for pass 1, which is given by 0.6 times N, which we just calculated 190.98 equals, and you're just gonna do the calculations. This 0.6 divided by 400, or with the 400, this is gonna give us the 3.5 minute. Make sense? So this is the machining time for pass 1. we still need to calculate the meter removal rate, which it should equal to the VF times D, right? So V, which is the cutting speed, was given by 30, but it should be multiplied times 1000 to convert from meter per minute to millimeter per minute, times the feed, which was given in best 1 by 0.6, times the depth of cut. The depth of cut, D1, we can calculate it here. It should equal D0 negative D final over 2, right? D0 was 50, negative D final, which is 46 for base 1 over 2. This definitely is going to give us 4 millimeter, right? So because the difference, no, it's going to be 2 millimeters. Yes, the difference here it is 4, so it's going to be like just 2 millimeter as depth of cut. Make sense? So this is going to give us 2 millimeter. Doing the calculations, this is going to give us the 0.6 times 2 times 1000 times 30 equal 36,000 millimeter cube per minute. This is going to give us the meter removal rate for the first pass, which is MRR1. This is for the first pass, and we just finished this pass like we already worked over a separate problem. Now we're going to move to another problem, which is pass 2. For pass 2, your objective is just to calculate the meter removal rate. You're gonna start from scratch. LCF over divided by F times N. Don't think that N will be the same. No, it will be different. Even if we are still using the same V, if this V is the same as this one, N will be different. So you have to calculate from scratch, even if we already still using the same cutting speed. Okay, so we're gonna calculate it. LC will be the same one since we don't have anything regarding the approach or the over travel distance, but we need to calculate N. So calculating N is gonna be 1000 times V divided by D0 for the second pass. 1000 V for the second pass, it is 20 meter per minute divided by pi D0. Even though if you're still using the same theory, because D0 here is different than there in the second pass, N will be different, even if we're still using the same V. So D0 here it is 46. So you have to calculate it again. So 1000 times 20 divided by 46 divided by shift pi, this is gonna give us 138.4 RPM. Then LC, we said that it is already LW plus the approach plus the over travel, which already 0, so we're gonna end up with 400 millimeter as we calculated before. Then your objective is just to plug this data here to end up with the machining time. TM will be 400 divided by the F, which is the feed for the second pass, which was given by 0.05 times the times the cutting speed, which we just got it by 138.4, and then your objective is just to do the calculations. This is gonna give us the 0.05 divided by 400, and this is gonna give us 57.8 minutes. As you can see, we're gonna take longer time for the second pass. This is TM2 for the second pass, which is gonna be longer. Here we're gonna take only 3.5 minutes, and we're gonna remove 4 millimeters of the diameter. Here we're just gonna remove only 1 millimeter of the diameter, but it's gonna take very long time. Why? Because we are using a very small feed. It means that this finishing operation is gonna take very long time, and this increase the cost of the part. This part will be very pricey. Because of what? Because of it is finished, so it takes long time to perform this operation. How about the second meter removal rate? The second meter removal rate is going to be the V times F times D, the same equation. So V is in the second pass, it's going to be 20 times 1000 to convert from meter to millimeter times the feed, which is 0.05, which is the small feed, times the second depth of cut, which was already given to us by 0.5. So this is going to be 0.5 here. Doing the calculations, you're going to end up with 0.5 times 0.05, 1000 times 20 This is going to give us 500 millimeter cube per minute. This is going to be the meter removal rate in the second pass, right? So the question is, since we do have in the first pass TM1 with 3.5 minutes and the meter removal rate with this value, and this is the meter removal rate for the second pass, and this is the machining time 57.8 minutes for the second pass. So the question is, what should be the total machining time of the entire turning operation? We're still working over two passes, but we're still working over the same turning operation. So what will be the total machining time? Definitely is going to be the machining time 1 plus the machining time 2, which is going to give us your objective is just to sum the 57.8 plus 3.5. This is going to give us the 61.3 minutes, 61.3 minutes as the total machining time to perform the entire turning operation. But the question is, what should be the total meter removal rate? Is it the sum of the MRR1 and MRR2? No, the meter removal rate cannot be added, cannot be summed together. Why? Because it is a rate, and this rate will be different. So what does it mean? It means that we are using a very high rate of meter removal in the first pass, and in the second pass we are using a different rate, and the rates cannot be added. We cannot add the meter removal rate 1 to 2 to end up with like a total meter removal rate, but we can calculate like an average between both of them, which also not practical, and we are not doing this thing. But the meter removal rate cannot be added. Why? Because there is no physical meaning to the new value. We need to know the meter removal rate for every individual pass. So for pass 1 will be with a value high rate, in the second pass the rate will be decreasing, right? But the machining time can be added. Make sense? So don't add the meter removal rate together. When you ask it to calculate the meter removal rate for such a problem, your objective is just to find the meter removal rate for pass 1, for pass 2, and that's it. But the total machining time, it should be added together to give 61.3 to finish the entire process over the two passes. Make sense? So this is simply how we can calculate, and over these 3 examples, we doubly explained how we can calculate the machining time and the meter removal rate for the turning operation. For now, let us move to the machining time and meter removal rate for the drilling operation. We mentioned before in the drilling operation that you're going to have a twisted drill like this one, and this twisted drilling is going to rotate. So the rotation of the twisted drilling, this is the cutting motion. And in the meanwhile, it will be fed into the work bar to penetrate, opening a hole into the work bar. So this vertical motion perpendicular to the surface of the work bar, this is going to give us the feed motion. Make sense? So, and again, these are the 2 working motions, and we should be given like a cutting speed. In addition, we should be given feed, very similar to the turning operation. And the objective again is to calculate how long it would take to open a hole using the link operation. Whatever this hole it is, through hole like this case, or blind hole. This is blind hole, but this one is a through hole. Make sense? So to calculate the machining time, this is going to be the same equation, which is LC over FR, or which is the multiplication of F times N, which is going to be typically the same equation, the same one that we use for the turning operation. As I mentioned, this equation is used with all the machining operations. Something that you should understand, I forgot to tell you about it in the turning operation, that this LC actually, it should be the length of the feed motion. It should be the length, generally speaking, it should be the length of the feed motion. So what does it mean this? It's gonna be very clear. Let us talk about this. Actually, in terms of F, which is the feed, is gonna be the same. The feed F, it should be in millimeter per revolution, which it means that with one rotation of the twisted drill, this twisted drill, it should be penetrating and moving down with the feed value. For example, if the feed was given by 0.1 millimeter per revolution, it means that as long as the with one rotation of the twisted drill, the twisted drill, it should be penetrating, moving down 0.1 millimeter into the work part. If the feeder is higher, like let's say 0.5, so it's gonna move with one rotation. With one rotation of the twisted drill, it should be penetrating, moving down 0.5 millimeter into the work part. Make sense? So this is the physical meaning of the feed motion here for the twist, for the drilling operation, which is very similar to the turning operation. And again, the N is going to be the cutting speed, which it should be revolution per minute, but in many of the cases V will be given, which is the cutting speed will be given in terms of meter per minute, very similar to the turning operation. So if so, you're going to multiply times 1000 V divided by pi over D. What is D? D should be the hole diameter, which definitely is going to be the twisted drill diameter, because if you're already opening a hole with diameter 10 millimeter, you have to use a twisted drill with the same diameter as the hole. Because if you're going to use another twisted drill, you're going to end up with another hole diameter, right? So all the time the diameter of the hole, it is the same as the diameter of the twisted drill. So if he mentioned in the problem that the twisted drill diameter or the diameter or the hole diameter both are the same thing, and you're gonna, which describe D, you're gonna plug it here, you're gonna end up with N, which is gonna be the cutting speed, but in terms of RPN, if you multiply F times N, this is gonna give us the denominator to calculate the machining time. Make sense? But how about the length of the feed, or LC, or the length of the cut? So the length of the cut is going to be the whole length in general, but accurately it should be how long of feed motion that you're going to perform. What is the length of the feed motion? So for example, to open a through hole, and this is something that you should understand here, to open this hole, the twisted drill, assuming that it's gonna start from the beginning, from this point here. So it will continue going down, going down, going down. So one would think that this point, it will be moved here, right? Up to this point. So if we did so, the twisted drill will be here, and because of this triangular tip, this part won't gonna be removed and this part will not be removed. Both won't gonna be removed. It means that to completely remove these parts, this line, this horizontal line here, it should be moved up to here, right? Makes sense? It means that this step, it should be moved down farther to have like this horizontal line, it will be like kind of here, right? So we're gonna make sure that we already completely opened this through hole. So the total distance that this point, this twisted drill should be moving, it should be this entire distance. This entire distance, definitely it should equal to the LC in the equation. But also, as we explained before, we may add, in addition to this entire distance, we may add some approach distance. It is not necessary for the twisted drill to start directly from the surface. It would start from above a little bit with 1, 2, or 3 millimeters. The same thing, it is recommended to move down like this line. It is not necessary to be exactly where this line. We have to add like an over travel distance, right? We're gonna add here like another over travel distance. So the entire distance, it should be here. We're gonna add like another over travel distance here, in addition to another approach distance in the beginning. So we're gonna have this like over travel, and this is like approach distance, AP. Okay, make sense? So just let me represent this thing a little bit different, so it will be clear for you that in this twisted drill will be moved down up to here, let's say, and we're gonna have this triangular tip, and assuming that this extra distance is gonna be as over travel distance, this over travel distance is gonna be like kind of 1 millimeter, for example, 2 millimeters, up to at maximum 5 millimeter. The same thing we would add here in the beginning, some approach distance. This approach distance also, it would be like 1 millimeter up to 5 millimeter. In addition, so if we decided to calculate the total length of this total distance that this part or this step has been moved, this is going to be the total length LC. So how much it is? This LC actually it should start from here, right? So this should give us the entire LC kind of. Makes sense? So how much is this LC? Let me remove this part. So the question is, how long is this LC? LC. So based on this, we're gonna conclude that LC is gonna be the approach distance, right? Plus the thickness of the work part, which is T. This is the thickness of the work part, plus here we are opening through hole, right? Plus the over travel distance, plus this distance that we're gonna give it a name as A. What is A? It should be this distance of the triangular shape, this A, which is already given here as A. This A is not an approach distance. This is just depend on the geometry of the tip of the twisted drill. So adding all of these parameters together, you're gonna end up with the LC, which should be substituted into this equation. Make sense? This is in case that we're already working as through hole. For a blind hole, we're gonna have a little bit different things. So let us split it to, then we're gonna discuss later the blind hole. Make sense? So this is for the LC. As we mentioned before, if the approach distance was not given and the over travel distance was not given, these two terms will be zeros. T definitely is gonna be the thickness of the work part, and we still need to calculate A. So A is gonna be the equal to the D over 2 divided by the tan inverse of phi over 2. Why? For example, this A, which is this distance, so let us work over this triangular shape on the side here, just to show you how did we calculate this A. So this triangular shape, we would like to calculate if we split it twice and assume this angle is going to be, definitely this angle is going to be 90 degrees. So this height, this distance here, this is going to be A. And this distance definitely is going to be D over 2. Why D over 2? Because this entire distance is going to be the twisted drill diameter, right? So if this is the diameter of the twisted drill, this definitely is going to be half of it, right? Which is D over 2. So this is going to be, just make sure that it is very clear. So this is going to be D over 2 in this way. How about this angle? This entire angle is known as the point angle of the twisted drill, and for many of the twisted drills this would be either 118 degrees or 120 degrees, and this is the very common thing. So this point angle, if it is not given, you're gonna use this one, use this 120 all the time. So this indicates that this a little bit small angle is gonna be 60 degrees, which is gonna be half. This angle is gonna be half. This angle here is gonna be phi over 2, half of it. So if I ask you to calculate A from the geometry of this triangular shape, so what should be A? So definitely A, it will be D over 2 divided by the tangent of phi over 2, because if I ask you to calculate the tangent of this angle, it's going to be the opposite divided by the adjacent to the angle, which is going to be D over 2 divided by A. So A will be D over 2 divided by the tangent of phi over 2. And phi, as I mentioned, if it is not given, and in many of the cases it won't going to be given, you're going to deal with it like 120. It means that this is going to give us the tangent of the 60 degree, and D again, this is the twisted drill diameter, which is the same as the hole diameter. So you can simply calculate A, add it here to T. If the over travel or the approach distances were given, you're going to add them. If not, they are zeros. You're going to end up with LC to calculate the machining time. Make sense? This is in case that we have through hole. For a blind hole, it's going to be much more easy. Why? Because for the blind holes in general, it means that the hole, it should be with a specific depth. But here we're gonna open a through hole in a work part with a certain thickness, so T will be given. But here for a blind hole, it is the thickness of the work part will be bigger than the depth of the hole. So the depth of the hole will be exactly given. It means that this depth D will be given. This is the hole depth or hole length will be given to you. So your objective is just to plug this one. So directly LC that we're gonna use in the equation up there will be D plus the approach distance. Here we cannot add any over travel distance. There is no over travels here. There is no over travel distances. We cannot add over travel, but we can have approach distance. It means that it is not necessary to start from here. We can start a little bit up with some approach distance. So if this approach distance was given, you're gonna add it to the depth of the hole. You're gonna end up with LC. Directly, you're gonna calculate the machining time. Here, even there is no need to calculate A, which is that depend on the geometry of the twisted drill. There is no need to calculate it because the depth of cut will include A automatically. A, this value, this distance were included in the depth of the hole as explained in this figure. Make sense? So something that you should understand here, that you should distinguish whatever you're already dealing with a through hole or a blind hole in the given problem. Make sense? So this is how we can calculate the machining time. Nothing new except is to how to know that you should know how you can calculate the LC for either through hole or blind hole. How about the mirror removal rate? It's gonna be this formula for the mirror removal rate. It is pi over 2 d squared d. Again, this is the hole diameter. This is the hole diameter, which is gonna be the same as the twisted drill diameter. This is the twisted drill diameter. So either he gave us the diameter or the hole diameter. You for the twisted drill, you're gonna plug it here, F times N, which is the same Fn, which is the feed rate, the same feed rate as the denominator of the machining time. You can directly calculate the meter removal rate. If you need to know the depth of cut for some reason, but in many of the cases won't gonna be required, and actually this D, the depth of cut, we didn't use it. Don't mix between this D and this one. This one here, the depth of cut. This is the depth of cut, which is different than this D. Okay, so don't be confused. The depth of cut, that's something that you should understand about the drilling operation, that the depth of cut, it is half the diameter of the twisted drill as long as we're already opening a new hole. Make sense? So these are the equations for the drilling operation, and now let us consider these examples to explain how we can use them for the calculation of the machining time and the meter removal rate for a turning operation. Alright, for this example, we do have 50 millimeter through hole. So he directly mentioned that this is through hole. 50 millimeter is to be drilled. So this 50 millimeter, definitely he talks about the diameter of the hole, because 50 millimeter hole, he talks about the hole, and the thing or the geometry that distinguish the hole is its diameter. So it means that the diameter of the hole here was given by 50 millimeter, which is uppercase D, and it is through hole as he just mentioned here. It means that we have to calculate the A, in addition adding approach and over travel if they were given, to be drilled in a slab with a thickness. So this is gonna be T, which is the thickness of the slab part in which we shall open this hole. And the cutting speed, remember that the cutting speed would be given either N or V, depends on what? Depends on the unit. Here it was given as V at 30 meter per minute. And the feed, which is F, was given by 0.6 millimeter per revolution. It means that it is F, not feed rate, not FR. The drill approach this is the approach distance here, was given by 0.55 millimeter. And over travels by, so this is the over travel distance, was given by 2 millimeter. Remember, if they are given, that is fine. If not, you're just gonna cancel them. Determine the drilling time, which is the machining time, how much it is, and the meter removal rate, MRR, how much it is. Make sense? So To do the calculations, let us calculate first the machining time. Write the equation. It is LC divided by the F times N, or the FR. So we have to calculate N. N, it should be 1000 times V divided by D, and it is 1000 times V, which was given by 30, divided by the diameter of the twisted drill was given by 50. Doing the calculations, you're gonna end up times 1000 divided by 50 divided by shift pi, which is gonna be 190.98 RPM. This is N. Now we need to calculate LC. We are already working as through hole. For through hole, we're gonna add the approach distance plus the over travel distance plus the thickness of the slab plus the A value, which depends on the geometry of the twisted drill. So we have to calculate A first. A should be D over 2 divided by the tangent of phi over 2, which is the point angle. The point angle is not given, so we're going to deal with it like 120 divided by 2. This is going to give us 60 degrees, so this will be tangent of 60 degrees. And this definitely, the diameter of the twisted drill was given by 50, so it's going to be here on the top 25. Doing the calculations, 25 divided by the tangent of 60, this is going to give us 14.43 millimeter. This is going to be A. Adding all of these values together, so we're going to have here this approach distance, it is 0.55, the over travel it is 2, and the thickness of the slab was given by 60 millimeter, right? And we just calculate this value by 14.43. Doing the calculations, you're going to end up with LC in terms of millimeters. So this is going to be the length of the cut, which will be plus 2, 0.55 plus 60. This is going to give us the 76.98 millimeter. Then plug this data into this equation for the machining time. We're going to end up with the machining time will be 76.98 divided by the feed, which was given by 0.5 millimeter, 0.5 times N, that we just calculated 190.98. Doing the calculations, you're gonna end up with this value by 0.6718 minutes. This is gonna be the machining time to open this one single hole. Assuming that we do have like 100 times this hole, like we do have 100 holes identical the same, that they're gonna be done over the same twister, using the same twister drill with the same cutting speed, the feed. So what should be the total machining time? Multiply this machining time of a single hole times 100, which is the number of holes. Make sense? But here this was not required, so anyway we're gonna have only one machining time and that's it. And the meter removal rate, it should be pi over 2 d squared times F times N, as was already defined up there for the drilling operation. So it is pi over 2, the diameter of the twisted drill is 50 square, times the feed, which was given by 0.6, times the N, which we just calculated 190.98. Doing the multiplication, and here there is no need to do any unit conversions, so we're gonna end up with 190.98 times 0.6 times 50 times 50 times 0.4 divided by 4. This is gonna give us the 224,993.0 millimeter cube divided by minute. So this is gonna be the meter removal rate that it should be removed per unit minute to open this hole. Make sense? So this is, for example, again it is through hole, so we added approach and over travel distances. In case that we do have the same example, but for the case that we do have a blind hole, so instead of giving you the thickness of the slab and the over travel distance, even if the over travel distance was given, don't add it for the blind hole. For the blind hole, you're gonna have only approach distance plus the depth of the hole. So you're just gonna add both of them together, even if the over travel distance was given, which doesn't make sense to give you the over travel distance, by the way. But anyway, if it is given, don't add it, because we cannot add over travel distances to a blind hole. Makes sense? So the only difference in case that it is a blind hole, you're just gonna add D, which is the depth of the hole that will be directly given to you, plus the approach distance in case that it was given. Then you're gonna calculate LC, and the rest will be the same, typically the same. Make sense? So this is for the drilling operation, and now let us move to the milling operation. And this is gonna be the last type of machining operation that we're gonna consider the calculation of machining time and metal remover rate for. So for the milling operation, the machining time, it seemed that I forgot to write the equation, but anyway, the machining time is going to be the same formula as I mentioned. This one is fixed for all the machining operation, LC divided by the feed rate. And again, this LC, it should be the length of the feed motion. So to just remind you with the milling operation, in the milling operation, we should have a tool. And especially if we're gonna work over the face milling, we said that we do have like peripheral or plane milling, and we do have the face milling. So for the face milling, you're gonna have a tool, and this tool will be with multiple cutting edges. So there is a multiple point cutting tool like this one. So all of these are different cutting edges or different teeth of the cutter, of the cutting of the milling operation. So this is going to be the cutter, and you're going to have here the work part. And the one of the specification for the conventional face milling operation that the diameter of the cutter, it should be bigger than the width of the workpiece. So this is going to be W. W here stands for the width of cut, which is going to be the width of the work part. As long as we are performing the conventional, the conventional face milling operation, that the diameter of the cutter, this D, it should be the diameter of the cutter, it should be bigger than the width of the work part. This is going to be the work part. Make sense? So if the cutter rotates, the rotation of the cutter, this is going to be the cutting motion. So again, it will be rotating with N in terms of RPM, or V in terms of meter per minute, or RPM. As we mentioned, typically the same over the previous examples or over the previous machining operations. And in the meanwhile, it will be keep, like milling over the surface, like sweeping over the surface. It's gonna keep moving over the surface of the work part. So the movement of the cutter, this is gonna be the feed motion, which would be defined here as either F in terms of millimeter per revolution, or FZ in terms of millimeter per tooth. So what is FZ? This is the feed per single tooth of the cutter, but the feed in terms of millimeter per revolution, this is the FZ times the number of tooth of the cutter. Make sense? Or it would be defined as FR in case that it was given as millimeter per minute. So again, all of these are three different forms. Here we do have a new form of the feed that you would be given the feed as millimeter per tooth, and instead of giving you the feed in terms of millimeter per minute or millimeter per revolution. This is distinguished for the multiple point cutting tool. But if you multiply it, something that you should understand, that the F, it equal the FZ times N, right? Or times Z. Z here stands for the number of teeth of the cutting tool that would be given. So if you multiply, so if you were given the FZ, which is the feed per single tooth, and you multiply times the number of tooth, you're going to end up with the total feed per revolution. Then if you multiply times N, which is the rotational speed of the cutter, you're going to end up with the feed rate. So to calculate the machining time, we need in the denominator here the machine rate, the feed rate, which should be in millimeter per minute if it is not given in this form, and instead you will given FZ as millimeter per tooth. So you have to multiply times Z times N. N, which is going to be the rotational speed, the cutting speed in terms of RPM, as we mentioned before, in case that the V was given by meter per minute, So you will have to multiply it times 1000 divided by pi times d. D, this stands for the cutter diameter, which will be given to you. Then you're gonna calculate N to multiply times Fz times Z, which is the number of teeth of the cutters of the cutter. You're gonna end up with the feed rate, plug it here in the denominator. But how about LC? This should be the length of cut. Here in this schematic, I'm explaining the length of cut. It should definitely equal to the length of the work part. This is gonna be the length of the work part, L, and this is gonna be L, the length of the work part. But this W, this width is gonna be W, which is gonna be the width of the work part. So the how long in terms of distance that does this cutter is going to move it, this cutter is gonna start from here and move all the way this direction up to here. In case that we're already performing finishing, we said that we may have rough cutting or finishing cut, right? For the finishing cut regime, that you're gonna move from here and you're gonna add here like an over travel distance, approach distance, I'm sorry. You're gonna add here like approach distance, and on the other side, you're gonna add another approach distance, over travel distance, right? So you could consider that exactly to be more accurate. This is gonna be the approach distance, and this is gonna be the over travel distance and approach distance. Make sense? If we're already performing a finishing operation, if we're already performing rough cutting, there is no need to have over travel. There is no need to have the over travel, so distance, and even there is no need to move the tool outside the surface. It means that you're just gonna move up to the center. We're gonna move the center up to the edge, but here we have to move to the center outside the tool, up to be outside the tool for the finishing operation. So the difference between the finishing and the roughing operation makes these differences here. Like this LC will be with this form, where LW, which is gonna be the length of the work part, the original length of the work part, and we're gonna add two values here over the both sides, A and B. Where A, this is the sum of the approach and over travel distance. This A and B is the sum of the approach and over travel distance. This a little bit small distance, and here over travel distance. But here there is no over travel for the rough cutting, but we may have here approach distance. So B, it should equal to, this is the approach plus the over travel distance. So you're gonna sum them. So if the approach and over travel distance, you're gonna sum them and plug them here for B, which typically it is between 2 up to 5 millimeters, depends on the given data. But A, this A, it's gonna be D for the case of finish milling, and it's gonna be half D in case of rough milling. Half D, D stands for the diameter of the cutter of the cutting tool. Or the cutter of the milling operation. So half of it for rough milling and D for the finish milling. You're gonna add A here to the B to the length of the cutter, the work part, to end up with LC to calculate the machining time. Definitely is gonna be in minutes. So this is simply how we can calculate the machining time for the milling operation. For the metal removal rate is gonna be the LWD. D stands for the depth of cut, which will be directly given to you. There is no specific formula to calculate the depth of cut, because this is the penetration of the tool into the surface of the work part. How deep that this tool will be penetrating inside the work part. This is going to be the depth of cut that should be given to you. And the LW, this is the length of the work part. W is going to be the width of the width of the work part divided by the machining time that we just calculated. You're going to calculate the metal removal rate as millimeter or per minute or meter per minute, depends on the unit system that you're already using for this, the calculation of the metal removal rate. So this is for the equation. Now let us consider this example of face milling operation. Face milling, it means that this is the kind of configuration that we're gonna use. There are some a little bit different formulas for or changes in case that we're already working as plain milling, but we're not gonna consider this part. We're just gonna focus over the face milling, which is gonna be very similar but with a little bit different things. But the key idea is just to give you how we can how you can calculate the machining time and metal removal rate for a milling operation like face milling operation. So in the face milling operation, the work part, the workpiece top dimensions were given by 100 millimeter by 250 millimeter. Like you already given a work part with a length of 250 millimeter. This is going to be the length of the work part, 250 millimeter, and the width was given by 125 millimeter. So this is going to give us LW was given by 250 millimeter, and the W was given by 125 millimeter. The cutter is 150 millimeter in diameter, so this is going to be D uppercase for the cutter, 150 millimeter diameter, and has Z equals 8 teeth. So this is the number of teeth of the cutter, and rotates by 300 RPM. So this is the rotation of the cutter, this is the cutting motion, and the cutting speed. The cutting speed was given by 300 RPM, so that's why it was N, not V. The depth of cut, which is D, was given by 3.125 millimeter. This is the depth of cut, and the feed. Remember that you have here for the milling operation, we do have three possibilities for the feed. The feed would be given as millimeter per tooth at this case, so it should be FZ as 0.125 millimeter per tooth, or it would be given as millimeter per revolution, so it's going to be just F, which is the multiplication of FZ times Z, or it would be given as feed rate as millimeter per minute. Determine the milling time, which is the machining time, how much it is, and the metal removal rate, how much it is. For the two cases, for the case of rough milling and finish milling, so like you're gonna work over two separate problems. So let us start with the rough milling. So again, you're gonna work over this one like two separate problems. In the rough milling, you're gonna use the same conditions here. For the only difference between rough milling or finish milling actually is the calculation of LC. The LC for the rough milling, or for both cases, it should equal to the length of the work part plus the approach, the A distance plus the B distance. This B should be the sum of the approach and over travel, but here it should be given. He didn't, this B, it should equal to the approach plus the over travel, and both were given. He didn't mention anything regarding the approach or over travel distance, so that's why B will be 0, but A will be D over 2 for the case of rough milling, and this is what we're already calculating. So the diameter of the twist of the cutter, it is 150, so it's going to be 75 millimeter, and then you're going to add it to the length of the work part. So we're going to end up with the LC at the length of the work part, which was given by 250 millimeter time plus the 75 is going to give us 325 millimeter. Make sense? Then you're going to calculate the machining time as LC divided by FR, right? So we need to calculate FR. FR is equal to the FZ times N times Z, right? So the FZ was given by 0.25 times N, which is the RPM were given by, was given 300, and Z, which is 8 teeth, the number of teeth of the cutter. Doing the calculations, this is going to give us 300. 0.25 is going to give us definitely the 300 millimeter per minute. Okay, so plug this data along with the LC, so we're going to end up with the machining time for the rough operation will be the LC, which 250 divided by the 300. Doing the calculations, you're gonna end up with the 1.0834 minutes. This is for the rough operation, so this is the rough machining. This is for the rough. And for the finishing, also we're gonna calculate, because he required actually the determine the milling and metal removal rate. So he required the metal removal rate. So the MRR for the rough operation will be divided by the milling operation. On the top we should have the length of the work bar times the width times the depth of cut, right? So the length there is 250 times 125, which is going to be the length and the width, times the depth of cut, which was given by the 3.125, so 125 divided by the machining time that we just calculated. You're gonna end up with something in terms of millimeter cube divided by minute per minute. This is gonna give us the 3.25 times the 125 and the 250. This is gonna give us the 9,000 or 90,144 millimeter cube per minute. This is the meter removal rate for the rough milling operation. Now we're gonna repeat the calculation, but for the finish milling. For the finish milling, nothing will be different except the LC calculations. So when we calculate the LC is gonna be the LW plus A plus B. So it's gonna be LW plus A plus B. B still 0. This is gonna give us 250 plus D 150. Here we're gonna consider the entire diameter, not half of it for the finish milling. So this is gonna give us the 400 millimeter, but still the feed rate will be still the same. It won't gonna be different, but because he didn't split it, he's still using the same machining conditions for both of them. But if the feed would be different between finishing or rough milling, finish milling or rough milling, so definitely you're gonna apply calculate again the feed rate for the machining time. So the machining time will be the LC, which is 400 over the same denominator that we used here, which was the 300, because we're still using the same parameters. So we're gonna end up with 4 over 3, which is gonna be 1.34 minute. This is gonna be the machining time. Since the machining time had been changed, definitely the meter removal rate as well for the finishing operation will be different. So this is gonna give us the LW and the W times D divided by the machining time, which is gonna be the LW, which the same values that we calculated, which is 250 divided by 125 times times 125 times 3.125 divided by 134. This is gonna give us this value here of divided by 1.34, which is gonna be 72.877 millimeter cube per minute. Make sense? So this is the machining time and meter removal rate in case that we already performing finish milling or finishing operation. If we already performing rough milling, this is going to be the machining time and the meter removal rate. The question is, should we add the machining time of the rough to the machining time of the milling? No. These are like two different problems, two separate problems. These are not two separate bases of milling operation as we did in the turning operation. In turning operation, like we do have base 1 and base 2, so we have to sum the time for base 1 to the time of base 2. But here, this like two separate problems. I just give you this example to explain that in case that I ask you to do rough milling, so you're gonna, when you calculate A, the only difference is just when you calculate A, you're gonna use A as D over 2. For the finish milling, is gonna be just D. Make sense? So this is for the milling operation, and this is gonna be the end of this video. That the objective is just to explain to you what does it mean machining time, what does it mean meter removal rate, and to know how we can calculate them for the most common types of machining operation, like the turning operation, drilling, and milling operation. And this is what we already covered in this video. All right, so that's it for this video, and thank you, and see you in the next one.